So first of all, are there any questions about what was discussed yesterday? No? So basically, it's a continuation of what I was talking about yesterday. So I'll remind you about the outline. So this part we covered, phenomenology of the phase transitions, discussing role of symmetries, and also said a few things about spontaneous symmetry breaking. So I will continue from this point, and hopefully today, scaling and universality, that part I'll finish, and then the remaining talks on tomorrow. These are the two things that I'll try to discuss in those talks. So let's just get back to where we were. So this is where we were in the last lecture. First of all, I have to go a little faster because otherwise it will be difficult to cover at least in the bare minimum that I wanted to discuss in this lectures. So we talked about the symmetry of the Hamiltonian. These are operations under which the Hamiltonian function remains invariant. So that once you know what the system is, what the interactions are, these symmetries should be known to you. You can write down Hamiltonian, which will have some symmetries, and some examples I have given here: system of particles, system of spins, and so on and so forth. But the idea was that in many phase transitions, the symmetry of the thermodynamic state that you get in the ordered state, in the low temperature phase, are not quite the same as the symmetries of the Hamiltonian. The low temperature phase typically has a lower symmetry than the symmetry of the Hamiltonian. The high temperature phase typically has the same symmetry as that of the Hamiltonian, but the low temperature phase has lower symmetry. And this is what we mean by spontaneous breaking of symmetry. So I'll just give you some examples. I talked about this example in the last lecture. So today, let me just go into a little bit more detail of exactly what we mean by the symmetry of a thermodynamic state. Those of you who are a little bit familiar with statistical mechanics will know that when we talk about a thermodynamic state, we are not talking about a particular microstate of the system. Just like if you have in a room where the air is in thermodynamic equilibrium at some temperature, pressure, etc., the particles are moving around all the time. So this thermodynamic state doesn't correspond to a fixed microstate. Microstate corresponds to sort of specifying the positions and the velocities of all the particles. These things are changing all the time. So thermodynamic state is basically an ensemble of states. And what kind of ensemble you get, that depends on external conditions. Typically, one looks at ensemble at a fixed temperature, which is called the canonical ensemble. And here, the ensemble basically tells you about what is the probability associated with a particular microstate in that thermodynamic equilibrium state. So system is going through many different microstates when it is in equilibrium. Each microstate will occur with some probability. And theory is basically specifying what is the probability of finding a particular microstate in that ensemble, in that collection of microstates. So this is what I have written down here. This is one of the sort of fundamental results of statistical mechanics, where we look at a microstate of energy E, looking at different microstates N, and the probability of microstate N in the ensemble is given by exponential of its energy divided by kBT. Kb is the Boltzmann constant and T is the absolute temperature. And the probabilities, of course, have to sum to 1. So there is a normalization that one puts in here. Make sure that the probabilities sum to 1. And the value of any observable in that in the thermodynamic state is basically an average over all the microstates with this probability. Okay, so this is the basic concept of statmech, saying that when a system is in equilibrium, it's going through many microstates. Each microstate occurs with some probability. The probability depends on which ensemble one is talking about. In the canonical ensemble, probability is given by, this is known as the Boltzmann probability because the Boltzmann constant is sitting here. And the value of that particular quantity observable O that we'll measure in that thermodynamic state is an average over its value in all these microstates, weighted by this probability that I have given. So a thermodynamic state is then defined by these probabilities. And the symmetry of the thermodynamic state, now, if you want to examine that, you have to find out whether all states which are related to each other by symmetry. Related to each other by symmetry basically means if the Hamiltonian has the same symmetry, all these states will have the same energy. So this probability would seem to indicate that all of those states will occur with the same probability in the ensemble. But in reality, what happens is that when the system undergoes a phase transition, all the symmetry-related states do not occur with the same probability. Some states are seen, some other states are not seen. And that is basically what one means by spontaneous symmetry breaking. The Hamiltonian has a symmetry. That basically means that there are a bunch of states which are related to each other through that symmetry, which should have the same energy. And then according to the Boltzmann probability, they should have the same Boltzmann distribution. They should have the same probability in the thermodynamic state. But in reality, what one finds is that in the broken symmetry phase, all these states do not occur with the same probability. In particular, some states don't occur at all. And so that is what we mean by a spontaneous breaking of symmetry. And this is a concept which is emergent property. One could not have guessed that that is what would happen if one just looks at the Hamiltonian at its symmetry. So if I have a Hamiltonian and then there are a whole bunch of states which are related to each other by symmetry, which will have the same energy. And so just from the Boltzmann distribution, you'd expect that all of them will have the same probability. But in reality, that doesn't happen. And that is where this spontaneous breaking of symmetry comes into the picture. So let me just try to give that by this example of this Ising Hamiltonian, which I have talked about earlier. Here the Ising spins, sigma, each of these can take two values, +1 or -1. They are sitting on a lattice, and then they're interacting with some coupling constants. And one can put in a magnetic field if one wants to. So this is the Hamiltonian for the Ising model. And when the H is equal to 0, then you see that if I make sigma going to minus sigma for all I, the energy doesn't change. Right? This should be obvious because when I put this H is equal to 0, this term is not there. And you have sigma I, sigma j. If I change the sign of sigma I as well as the sign of sigma j, then the energy will not change. So the symmetry of the Hamiltonian for H equal to 0 is basically this operation. It's flipping all the spins. Sigma going to minus sigma for all I, that keeps the energy invariant. So that's a symmetry, discrete symmetry that we are talking about. Hamiltonian has this discrete symmetry. So these two states that you get by flipping all the spins, they will also have the same energy. So according to the canonical ensemble, you'd expect that these two states will occur with the same probability. But that doesn't happen when the system orders. When you have a phase transition and when you are going to a state where there is a finite magnetization, it basically means that these two states are not seen with the same probability, because if these two states are seen with the same probability, then the average of sigma would be equal to 0. Right? So this is what I'm trying to say here. If we look at, let's say, the ordered state where all the spins are up basically means sigma is equal to +1. And the other state where all the spins are down, sigma -1 for all the spins, these two states have the same energy, according to the Hamiltonian, when H is equal to 0. But to get a non-zero magnetization, you cannot have this, P of sigma I is equal to P of minus sigma I. Because then, by definition, you will have sigma I average is equal to 0. So what happens in the ordered state is that you see either this or that. You don't see both. And this is the situation where two states which are related to each other by symmetry operation of the Hamiltonian, and that by definition tells you that they have the same energy, they do not occur with the same probability in the ensemble that you are looking at. So, and this is what one means by spontaneous breaking of symmetry, where you are seeing that one is choosing, or a system by itself is choosing to be in the upspin sector or in the downspin sector. And once the decision is made, once it goes into the upspin sector, then it doesn't go to the downspin sector at all. It remains in the upspin sector, and that gives you a non-zero average value of the sigma and a non-zero magnetization. Yeah? Sorry? So paramagnetic state, these two are the same. Paramagnetic state has the same symmetry as that of the Hamiltonian. So the Hamiltonian symmetry is that when you flip the sign of all the spins, energy remains the same. So you will expect that they will occur with the same probability. And that is what happens in the paramagnetic state, high temperature phase. And that gives you sigma average is equal to 0. But as soon as you go to a temperature lower than the critical temperature, where the magnetization is non-zero, sigma average is non-zero, then you cannot have this. This will imply that sigma average is always equal to 0. So to get a sigma average non-equal to 0, you have to then either go into this sector or into that sector. Either or, not and. Yeah? So this is again an example where because you have a large number of spins which are interacting with each other, they go into this collective state, collective ordered state, which breaks a symmetry that was present in the original Hamiltonian. And this is one of the examples of this emergent property that I talked about at the very beginning, that you see things that are not quite expected according to what naive theory will tell you, but this happens because of a reason, and that reason I'll try to explain in this picture. So what is happening? It's happening. What I'm saying is that the system goes into either in the up sector or in the down sector. Up meaning +1 sector, and down meaning -1 sector. So the question is, let's say the system has gone into one of these sectors, and the two sectors here are distinguished between two colors. Red color says sigma equals +1. Green color says sigma equals -1. So let's say that we start with a situation where everything is red. The system has below TC and it has gone into an ordered state with a positive magnetization. So a majority of the spins will be up. Now the question is, I know that there is another state where the spins are down, which has the same energy. So the question is, the system actually, whether through its evolution, whether it explores that state or not. If it explores that state, then sigma average will be equal to 0. Then you cannot have a non-zero spontaneous magnetization. But idea, which was sort of first formulated by Peierls, says that if one goes into, let's say, all red, all up sector, then from there to go to the all down sector, basically system has to go to an intermediate state where some of it is up and some of it is down. And this is a trivial argument that start with a state where majority of them up, and if you want to go from there to a state where majority of them are down, then in between there has to be a situation where some of them are up, some of them are down. And so this is the picture that I have here. But to create such a state, you have to create what is known as a domain wall. Something that separates the part where things are red from the part where things are green. And it is very easy to see from the Hamiltonian that the energy required to create a domain wall like this is proportional to the length of the system. Because every time you're creating a domain wall, on this side you have a upspin, and on that side you have a downspin. And whenever you have up-down spin, there is an energy penalty of 2J associated with that. So to create a domain wall which spans the whole system, you need an energy of 2 times J times L. And this energy becomes infinitely large in the thermodynamic limit. So the intermediate state the system has to sort of go through, if one wants to explore both all up and all down states, will have such high energy that its probability of occurrence in the ensemble becomes arbitrarily small. This probability is exponential minus the energy divided by kBt. So the energy basically diverges because thermodynamic limit, L is becoming very large. So that energy is very large, and as a result, that prevents the system from exploring both the upspin sector and the downspin sector. And that is possible only when this L goes to infinity. So this spontaneous symmetry breaking will occur only in the thermodynamic limit. One can show sort of rigorously that if you have a finite system, then it never has this spontaneous symmetry breaking, because it can always explore both upspin sector and downspin sector. And since two macroscopic configurations related to each other by the symmetry operation, the same energy, so then that will make sigma average equal to 0. So this is an important conceptual point, that the system is exhibiting by itself spontaneously this breaking of symmetry between up and down. It's going into either the upspin sector or the downspin sector. and once it makes that choice, then it doesn't explore the sector where all the spins are reversed. And the reason, one of the reasons, I mean, this is a hand-waving reason, but one can make it more rigorous by doing rigorous mathematics, is that that doesn't happen because the intermediate state the system has to go through to explore both sectors will have energy which will diverge in the thermodynamic limit. So that process doesn't occur. And so it remains in the either upspin sector or in the downspin sector for all observable times. So I hope, this argument makes sense. One thing that I wanted to show, and that might be amusing, is let's see if I can show a movie. One is doing a simulation of this two-dimensional Ising model where there are two colors that are used to denote upspin and downspin. There is a blue color, which is, let's say, upspin, on the white color, which is downspin. So we start with a situation where you have equal number of up and down spins, and then one is following what is known as the Monte Carlo dynamics. I don't want to go into details of that. That tells you about how the states change as a function of time. And one is proceeding in time, and as you can see here, what is happening here is that there is a separation. That you have islands of, let's say, the blue phase in a background of white, and system has then made a choice to go to the phase where majority of them are going to be white. And eventually, as time progresses, you see the blue part shrinks, and gradually you'll see that eventually at very long times, the whole thing is going to be mostly white. There are little patches of blue somewhere, but it will have a finite magnetization corresponding to the direction which is represented by this white region. So eventually, as you see, the blue domains are decreasing, and although there are the big domain here, which will take a long time to decrease, but eventually you'll see that this green part will essentially go to zero, and you will have a blue, essentially blue part, and there will be some little green things there, which is basically the system has chosen to go, depending on the initial condition, system has chosen to go into a state where majority of the spins are in the white part. It could have chosen the other way around also. That depends on the initial condition. But once it has chosen that, it will remain. When you've chosen to be in the majority white part, it will remain in the majority white part for subsequent times, because to go there from the majority blue part will take infinite energy in a thermodynamic limit. Fixed small system, finite system, that will happen. There will be switching back and forth between the two ordered states, which are related to each other by the symmetry. Okay, so this is a very important concept, and I'd like you to keep that in mind. This is one of the very important messages that one gets when one studies phase transitions, that the symmetry of the Hamiltonian is not everything. Thermodynamic state can actually break the symmetry of the Hamiltonian, and that is what happens when you go from the disordered state to the ordered state by changing some parameter like temperature or magnetic field or something. Any questions? Okay, then. So let me then this is the end of this topic related to symmetry. I'll not go there. One thing I wanted to mention was that whenever there is a transition like that, going from high temperature disordered state to a low temperature ordered state, one can define what is known as an order parameter, which is zero by definition in the disordered state, and which will be non-zero in the ordered state. So I have just given you some examples of such order parameter. And you have to be careful in defining the order parameter. You have to take into account the symmetry of the problem in defining the order parameter, in the sense that, as I just mentioned, there could be different ordered states related to each other by symmetry. Just like in the Ising model, we are looking at majority up state is one of the ordered state, majority down state is another ordered state related to each other by symmetry. So the order parameter should be such that it should have different values in these two states. It should not have the same value. So, and that is where the symmetry of the problem comes in. And so the order parameter has to be defined in such a way that, first of all, of course, it's called order parameter. So it means that it is zero in the disordered state, and it acquires non-zero value in the ordered state. That's the first thing. But then also to define the order parameter, one has to take into account the symmetry considerations and to make sure that different ordered states which are related to each other by symmetry will have different values of the order parameter. So the Ising ferromagnet that we just discussed, order parameter is a spontaneous magnetization, sigma average. Sigma average was positive value, means that majority of the spins are in the +1 state. Sigma average negative value means that the majority of the spins are in the majority down state. And these two, of course, are M and minus M. This distinguishes between the two symmetry-related ordered states. So if we have a more complex system like a ferromagnet, where the spins, instead of being ±1 variables, they are vectors. Then again, the order parameter is basically the average value of a spin, but this quantity is now not a scalar. In the Ising model, the order parameter is a scalar. It's just a number. Could be positive or negative. In this case, the order parameter will be the spontaneous magnetization again, but since the spins can point in different directions, you have vector spins, so the order parameter also will be a vector. I also talked a little bit about the crystalline, liquid to crystalline solid transition. The order parameter there is a little bit complicated, but if you think about it, this order parameter should tell you that the systems have gone into a lattice, a regular arrangement of the particles. So something which is non-zero for a regular arrangement, and but which is equal to 0 in the high temperature phase where the particles are distributed not in a regular manner. So that should be the order parameter. And one can check. This is something that, it's just to think a little bit about, you'll be able to figure that out. That if we look at the local density and take its Fourier transformation, and the k vector that goes in there is a reciprocal lattice vector, then this quantity will be non-zero in a crystalline state, but will be 0 in a liquid state. So again, one has to choose the order parameter in a particular way that it reflects the changes that is happening in the system. In the high temperature phase, disordered phase, it should be by definition equal to 0. In the low temperature phase, where some order has developed, it should give you a non-zero value, and it should also tell you about the basic symmetry that is being broken at this phase transition. So again, in these cases, it is fairly simple to come up with an appropriate order parameter. But one of the things that people sometimes spend a lot of time on is that experimentally we have seen some transition, and a little bit about what is going on there. And so, how to define an order parameter which will characterize that transition is always not so easy. So there are situations where the order parameter definition becomes quite non-trivial, and a lot of time, a lot of effort has to be spent to try to understand the ordered state and what is the order parameter that is right for that ordered state. But I'll not go into such details. I mean, I had some examples here, but since time is short, I'll not. So again, this is just a quick 5-minute introduction to the definition of an order parameter. So when you see a transition, if you want to characterize it, you want to study it, you want to understand what is going on, you have to first of all look at the symmetry properties of the state that one gets below the transition, and use that to define an appropriate order parameter, which will be 0 above the transition and non-zero below the transition. And there's simple cases like Ising model or Heisenberg ferromagnet, etc. It's fairly simple to do that, but I just wanted to also tell you that it's not always so simple. Okay, so this is, I think, the second topic that I had in the original list. We come to an end of that. From this point onwards, you will see people can read it, right? I mean, since this is being recorded broadcast, I thought it would be easier to actually show everything on the screen. So I have some handwritten notes, and I've just made scans of that, and I'm just trying to put that up. So as long you don't have any issue with reading what is going. So now we come to the sort of more finer characterization of these phase transitions, in particular, characterization of phase transitions which are continuous, which are not first order. Yesterday I was telling you about first order transitions where measured quantities have discontinuities, like liquid to gas transition, where the density will have a discontinuous change. But now we are going to specialize to continuous phase transitions, where the order develops continuously from the disordered state. And majority or large number of such phase transitions have been studied, and there one finds very interesting properties of various physical quantities. So now from this point onwards, unless there will be a few digressions, but most of the discussion will be about this continuous phase transitions. And the example that I already told you about is this Ising ferromagnet, where you have this plus minus one variables which are interacting with each other through a positive coupling constant. And then if you have your 2 dimensions or higher, dimension 2 or 3 dimensions, then at high temperatures, this system will show a paramagnetic phase where the sigma average is equal to 0. And then it will go to a ferromagnetic state where sigma average is non-zero. It could be both positive or negative as we go below a certain temperature. And I had also shown you this picture where in 2D, this was solved exactly. And you can see this, that the order parameter is the magnetization, right? And then you are plotting it as a function of temperature. H equals 0, no external magnetic field. So order parameter is equal to 0 at high temperatures by definition. That's how you define the order parameter. But as you go to a temperature lower than a particular value, then it begins to rise. Eventually, it becomes 1 at t equals 0. But this development of the order is continuous. There is no jump between 0 and some finite value as one crosses the temperature. So this is an example of so-called continuous phase transition. And as you can see here, there are some funny things going on here. Large fluctuations, specific heat diverges, internal energy has a very quick strong dependence on temperature, around this temperature and so on. And this behavior is known as critical phenomena. Critical phenomena is behavior of physical quantities near continuous phase transitions, where the order develops in a continuous manner from 0 as one changes some control parameter. And such continuous phase transitions, critical phenomena, are often characterized by sort of quantities which are known as critical exponents. So I just wanted to tell you about what these critical exponents are. And we'll see that the values of these critical exponents also define something known as universality class. So all these things are very important to understand as far as this continuous phase transitions are concerned. So here I've just defined critical exponents. And these are standard names. So everybody uses the same symbol to determine basically, or to express the value of the critical exponent that tells us about how the order parameter changes as you go from above critical temperature to below the critical temperature. So here, of course, the relevant parameter is the temperature. So the phase transition is happening when you are reducing this temperature, and happening at a particular temperature Tc, the critical temperature. And we are interested in the behavior near this critical point. So to describe that, often one defines what is known as a reduced temperature, little t, which is how far you are from the critical temperature. And you divide it by the critical temperature itself to get a dimensionless quantity. And the critical point will be where this little t equal to 0. And the critical region will be one in which this little t has a value which is small, close to 0. And we're interested in the behavior in that region, where the deviation from the critical temperature made dimensionless by dividing it by the critical temperature itself is going to be small. And this is the picture, I mean, my handwritten picture of what you just saw in the previous transparency, that if you plot the magnetization as a function of temperature, then it will be 0 above Tc, and then it will grow continuously from 0 as one goes to a temperature below Tc. And this continuous growth is characterized by the exponent which is called beta. So this is how one defines it. The magnetization is a function of temperature. This is reduced temperature raised to the power beta. Beta is a number which is positive, bigger than 0. So it says that as t is equal to 0, which is big T is equal to big TC, the m is equal to 0, but its growth below the critical point is governed by an exponent, and this beta actually is not just is not an integer 1 or 2 or something like that. It's a fractional value, which says that the behavior is sort of non-analytic. If I take a derivative, the derivative will diverge at the critical point. So this beta is one of the critical exponents that one would use to characterize this continuous phase transition. There are other critical exponents that I have defined here. Now, in the Ising Hamiltonian, one can include a magnetic field. And when the magnetic field is non-zero, so this is how we include the magnetic field. This is the term that we are discussing earlier, sigma I, sigma j term. But there is a term which is linear in the field. So this distinguishes between sigma plus 1 and sigma minus 1. So as soon as you put in a field, the up-down symmetry is broken. And the field is positive, then there will be a finite magnetization, positive magnetization. The field is negative, there will be a finite negative magnetization. So this is what is known as the conjugate field. It is conjugate to the order parameter. Order parameter is sigma average, and it's just something that couples to that order parameter in a linear way. So this H is called a conjugate field. And one can then look at, if instead of having, so this behavior will be there when H is equal to 0. When H is non-zero, there is magnetization is always non-zero because it distinguishes between plus 1 and minus 1. So it favors plus 1 or favors minus 1 depending on its sign. So and that always produces a non-zero value of sigma average. And there is no phase transition when there is a magnetic field. But so this happens only when this H is equal to 0. But as soon as you put in a value of H, then there will be a non-zero value of M even here, here, here. So now if I look at the susceptibility, which is how the magnetization depends on the magnetic field. It's a derivative of the magnetization with respect to the magnetic field. This actually one finds that this diverges at the critical point. Because at the critical point, near the critical point, above the critical point, m is equal to 0, when h is equal to 0. Just below the critical point, m is non-zero for even if h is equal to 0. So the change in m as a function of h is going to be something unusual at the critical point. And what one finds is that the susceptibility at zero field itself diverges at the critical point, and there is an exponent associated with that, and that is called gamma, critical exponent for order parameter susceptibility. So there is a beta which tells us about how the order develops. There is an exponent gamma which tells us about how the susceptibility corresponding to that order parameter diverges at the critical point. And similarly, one can define other critical exponents like the specific heat, which this picture that I showed, the Onsager exact solution, which shows that the specific heat itself diverges at the critical point, and there is a critical exponent alpha associated with that. So all of these exponents are positive. You see, little t raised to the power minus alpha, this will diverge when little t goes to 0, as long as this alpha is a positive quantity. So at least here, all the exponents that I'm defining here are positive. There are situations where there are alpha can be negative, there is a cusp and things like that, but those are not generic situations. Generic situation is where the specific heat diverges at the critical point with an exponent which is called an alpha. One more exponent that one can define, which is called delta, tells us about how the magnetization at the critical point depends on H. So at the critical point, when H is equal to 0, magnetization is equal to 0. It's a continuous transition. So magnetization initially is 0, and then it begins to grow as one goes to T less than Tc. At Tc, m is equal to 0 when H is equal to 0. But if I put an external magnetic field, m will no longer be 0 at any temperature. In particular, at the critical temperature, there will be some dependence of this m on H. And that dependence itself is non-analytical, and there is an exponent delta that one associates with that. So you see that I have defined this alpha, beta, gamma, and delta, some numbers, which then characterize the non-analytic behavior that one sees near this continuous phase transition. And one is often interested in the values of these critical exponents because these critical exponents define what is known as universality class of the continuous transition that we are interested in. So I have about 5 more minutes. So let me just then go to that. I hope this little hurried, but the important thing to remember is that if you have a continuous phase transition, then one has various singular behavior of thermodynamic quantities in the vicinity of that transition. And that singular behavior often characterized by power laws, divergences, and things like that. And these power laws are expressed in terms of critical exponents, alpha, beta, gamma, delta. There are two other exponents which maybe I'll define later on. But the values of these critical exponents define what we call a universality class. And this is another very sort of strange and very interesting fact about these continuous phase transitions, that the values of these quantities can be the same for two different systems which have very different microscopic description. So let me just get to that slide and then I'll try to explain. Yeah. So I've talked about these critical exponents. Amplitude ratios is something that you don't have to worry about right now. But the statement is that these critical exponents, which are just numbers, not integers, I mean real numbers, are found to be the same for several different phase transitions with widely varying microscopic physics. And examples are like this, that this Ising model that I told you about, where this is sigma takes on values plus or minus 1, that was originally invented to describe magnetic behavior. Sigmas there represent spin moments associated with some atoms, molecules, electrons, or whatever. So it was a model which was derived to describe magnetic phase transition, paramagnetic to ferromagnetic phase transition. But people later on found that if I look at other systems, such as liquid gas critical point, in the first picture that I showed, the liquid gas phase boundary that ended at a critical point. So that critical point, the transition is continuous. Along the line, transition is discontinuous, first order, but as we approach that critical point, you get a continuous transition. So one can use this description to characterize that transition. And one finds that that liquid gas critical point, the behavior that one sees near that is exactly the same as far as these exponent values are concerned with what one finds in the Ising model. Similarly, there could be phase transitions in binary liquids, binary alloys, etc., etc. And in all these cases, the critical behavior as expressed in terms of these exponents, alpha, beta, gamma, delta, turn out to be the same. So although the physical systems are very different, in one case one is talking about magnetic spins which are ordering, other case one is talking about, let's say, whether the two liquids are mixing or they are phase separating, etc., etc. So the microscopic systems are very different. But as far as the critical behavior is concerned, one finds that critical behavior expressed in terms of these critical exponents turn out to be the same in both systems. So there are these large groups of physical systems which exhibit the same critical behavior. By that I mean that the values of these exponents turn out to be the same in all these systems. Similarly, if I look at what is known as the XY universality class, there earlier, I mean, when you talk about the Ising model, we talk about just scalar, so just one component of the spin, which can be either up or down. But one can look at a two-dimensional vector. The spin can be thought, I mean, in some systems, the spins can be thought of as two-dimensional vectors, which will have two components, X component and Y component. And models involving such spins are called XY models. So here, again, magnetic system with this two-dimensional spins, one writes down this XY model to describe the critical behavior, general the properties of such systems. But the critical exponents, one finds that they're the same for these other transitions, superfluid transition in helium, then superconducting transition, then some liquid crystal transitions, etc., etc. So again, without going into too many details, I just want to point out that there are many, many systems, or not many, many, but certainly more than one, several systems, which exhibit the same critical behavior, although their microscopic physics is very different. And this fact is known as universality, that the critical behavior is to some extent universal determined by only a few quantities, which can be the same in all these systems which fall in the same universality class, but their microscopic physics may be very different. So just this is what one is saying. Critical behavior depends on a few relevant parameters, and I have just given you a list of such parameters which tell you about which universality class your particular system belongs to. So this is symmetry is very important. Whether Ising or XY or Heisenberg, that is very important. Other thing is very important is the dimensional space. Whether you're looking at a two-dimensional system or a three-dimensional system, their critical behavior will be different. And then also the range of interactions. When this happens only in interacting systems, so one can talk about whether only nearest neighbor interaction or spins which are separated by large distances, they also interact with each other or not. And depending on that, the universality class, values of the exponents, can change. So once these things remain the same, then critical behavior will be the same. And this is what is known as universality. And this is again one of the very sort of important properties of continuous phase transitions, that near the continuous phase transition, microscopic details do not matter that much. The things that will tell you about the critical behavior as governed by these exponents will be determined by these quantities. Doesn't depend on whether you are talking about spin systems or particle systems or superfluid systems or whatever. So study of phase transitions becomes, in that sense, more interesting, because if you can understand what is happening for a particular universality class, then it's not just one system. All the systems that belong in that particular universality class, then you have understood the critical behavior happens in all of these systems. So I just want to end this section with something that I just added yesterday. So again, all these things that I've been talking about are for equilibrium systems, magnetic systems, system of particles, liquid crystals, superconductor, etc., etc. But the same thing also goes for many non-equilibrium phase transitions. And there is one non-equilibrium phase transition that again is very, very well studied. That is a transition from laminar behavior to turbulent behavior. In a fluid, as you start the fluid or make the fluid flow with some velocity in a pipe, as you change this parameter, then the flow often goes from a regular flow, a laminar flow, to a turbulent flow. And this turbulence is one of the sort of very, very, very big problems in sort of non-equilibrium statistical mechanics. The transition from to turbulence is again very similar to these continuous phase transitions. And there has been a lot of work on what is the universality class of this transition from onset of turbulence. Again, one can define some critical exponents like this for that system. And the question is, then one asks, these critical exponents, what universality class do these critical exponents correspond to? And these people have now shown, paper which came out very recently, that this is actually in the directed percolation universality class. So as I said, just to make you aware of the fact that all this discussion of critical exponents, universality class, etc., is not restricted to equilibrium problems. There are many important non-equilibrium problems also for which one can ask similar questions. And in particular, what are the critical exponents that describe the onset of turbulence? What is the universality class that correspond to those critical exponents, etc., is a very, very important question, and people can address that here. So I think I have taken 5 minutes extra. So
we have a long break, so
okay.
we have a bit of so we have time for one question. We don't have time for one question, but let's take one question.
Yes. The students are not asking questions. I'm concerned about that. Yeah. I don't know.
Is it the same thing? Lowering temperature is equivalent to increasing the strength of interaction.
The quantity that comes into the picture in the Boltzmann distribution is J divided by KBT. J divided by KBT. So Hamiltonian, so I mean, you have the Boltzmann probability, which is exponential minus energy divided by KBT, right? So in the energy, the J comes in here. So the actual parameter that tells you about whether in the ordered phase or disordered phase is J divided by KBT, dimensionless quantity. So going to lower temperatures is exactly the same as increasing. Yeah. 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 So I mean, we have to look at dimensionless parameters, not parameters which have some value in some dimension.
Yeah, discuss it later. And I actually said one question because I also had. Thank you. And that was a very clear talk.
I hope, but I don't know whether this is getting through or not getting through. I hope it is. People are getting something out of this. I hope.
Have books available on these things, right? I mean, I know you gave to give one of our NPTEL courses.
NPTEL I have not given.
Yeah, I saw something on our website.
No, I mean, there are a series of lectures that I've given other places also. Here I have given several series of lectures.
Yeah.
So those are available on
Yeah, but you should give the resources, not give the resources, but at least give the reference to our students, because I think a lot of material, they need to go back and read stuff.
No, many years ago I gave a course in one of these ICTS RRI schools. So all these things are discussed there, so I can give them. And it's available on the web, so one can look at them.